As multi-robot systems become more prevalent, the problem of allocating tasks to these robots in order to maximize the performance of the system has received increasing attention in the research community. Recent works in this area have focused on incorporating real-world influences and effects, such as resource contention and interference, and uncertainty. In this paper, we developed a framework for calculating the cost of a particular allocation of tasks to robots in situations that have resource contention, as well as uncertainty in the task durations. It uses several approximation methods to quickly and accurately calculate probability distributions describing the times at which each robot is expected to start and finish its task. It is agnostic to the optimization method used, facilitates the use of any objective function, and can also be used in conjunction with chance constraints. The specific type of resource contention considered in this paper is mutually exclusive resources such as recharging points, and situations where robots cannot perform their tasks in parallel. In the most general case, the order in which the mutually exclusive resource is used depends on the order in which the robots arrive at that resource. When uncertainty in the robot's travel times to the resource is considered, all combinations of the possible arrival order of the robots need to be considered in order to accurately estimate the probability distributions of the task start and end times for each robot. Under the assumption of normally distributed uncertainty in the task and travel durations, we developed analytical methods for calculating the probability of a given arrival order of robots, and the task start and end times conditioned on that arrival order. Once these have been calculated for each possible arrival order, the probability distribution of the task start and end times can be calculated by summing the individual probability distributions for each arrival order, multiplied by its probability. Consider an example scenario with 3 robots. These graphs show the task finish times for each robot as calculated by the framework compared with a histogram generated using a Monte Carlo approach. Using this framework, an accurate probability distribution is calculated in only a fraction of the time required by the Monte Carlo approach. In a large-scale simulation example with over 100 robots, the developed framework produced more accurate cost estimates for the same calculation time as a Monte Carlo approach for up to 7 robots per mutually exclusive resource. Beyond 7 robots per mutually exclusive resource, the factorial increase in the number of potential arrival orders reduce the utility of the developed framework. Future work should therefore focus on developing methods for segmenting the problem so that the number of arrival orders that need to be considered can be minimized.